Over to you, Kirti. Ms.
Hello,
Kirti, you can
hello,
continue. You can continue.
hello. Am I audible?
Yes, you are audible.
Okay. So good evening, all. Today we are going to have a session on pile and pile cap designs. So in last class, there was a session taken by Reggie sir on footing design. So as a continuation, we are moving to the pile and pile cap design part. So here I'll be sharing my screen now. Is my screen visible?
Yes.
Okay. So we are going to have a hello.
Yes, you are audible, ma'am.
Okay, hello.
The screen is also visible. Okay. While Miss Kirti joins, we'll have a discussion. Okay, today's quiz you will have noticed that most of the questions were from previous quiz. So the main reason is that I wanted to check how much of you have refreshed what you are learning. Okay, we'll have such quizzes in between to know are you refreshing old portions or not. Okay, and I'll be checking the results thoroughly because I want to know are you keeping update on what we are teaching. Everything is linked, so you have to try to connect or revise accordingly. Okay.
Hello, hello. Am I audible?
Yes,
Hello, sorry
you
for
can
the delay.
continue.
Okay.
It's okay. You can continue.
Okay, so Now we are going to discuss about the pile and pile cap design. So I'll be uh, showing you with the help of a project that we have done earlier here. So this is a hello. Is my screen
Miss Kirti,
visible?
your screen has to be shared. It's currently off.
Okay, okay. Is it visible now?
Yes, you can continue.
Okay, so this is the model of a G+1 residential project that we have done here earlier. So for hello.
Yes, you're audible. You can continue.
Okay, so you can see the soil report here. This is a soil report. From soil report, we are arriving at a solution to know which type of foundation we have to use for a particular project. So this is the particular soil report we have generated for the this particular project. So this is a G+1 residential project. As you can see here, up to 4 meter, we have no good soil is found here. N values are really low. It's just 0. I think we have already discussed about the soil reports and foundation recommendations already. So at shallow depth, there is no good soil is found here. So the possibility of providing a shallow foundation is uh, not possible here. So we are moving to the pile foundation, means the deep foundation. So you can see here at 10.5 meter, we are having some n value. Even it is really low, we can have some value here. It is 1. So if we move to the recommendation part, it suggests we can have the double bulb under rimmed pile of 50 centimeter dia with a capacity of 130 kilonewton. 13 tons means 130 kilonewton. So we can have a uh, pile of 13 tons capacity at a depth of 10.5 meters. So accordingly, with this information, we will be creating the model here, and accordingly, we generate the pile design. So for the purpose of creating the design, we have to find the foundation reactions. So reactions we'll be getting from the model. I'll show you. This is the foundation reactions. So this Fz value means the total load coming on each column, beneath each column. So this means the total load means the total slab load, wall load, whatever load coming from the structure. Uh, the entire load coming from the structure is shown here, which is Fz. So we already know the loads coming on each column, and we know the pile capacity also. So by dividing the pile capacity, by dividing the Fz with the pile capacity, we will get the number of piles required under each column. So here we can have one column. So at all the column points, column locations where the loads coming is below 130, one pile is sufficient. So where the column loads are more than 130, accordingly, there will be a requirement of more than one piles. So accordingly, we have created the pile design, which is shown here. You can see there is a foundation layout showing the number of piles. At some points, as I earlier said, there is a requirement of only one pile, and at some points there is a requirement of more than one pile. Here it is a 2 pile, and at some points there is a requirement of even 3 piles under a single column because the load coming is really high. So accordingly, we have to increase the number of piles. And now you can see here, at some points it is given in just like I mean just horizontal. Here it is 90 degree, means vertical. But you can see here this T shape is given at some angle. Here also this pile group, 2 pile group is given at some angle. It is not 90 degree, neither it is 0 degree. So it is given at some angle. So why this is provided like this? Can anybody say? Here you can see this is a 3 pile group which is given in a proper direction, like ortho. But here you can see it is not 0 degree, it is not 90 degree. At some angle it is given. Why it is given like that? Can anybody say? Why there is an inclination of pile cap here? Can anybody say? You can give it like this, or you can give it like this. Here also we can, provide it like this. Light is given at some angle, at some inclination. Can anybody say? Why there is a tilt coming? Hello, am I audible?
I guess Kirti, they are not good enough to answer that question. You
Okay,
can
I
continue.
okay, I thought I am not audible. That's why I asked. Okay, so this is because between each pile, from one pile to the neighboring pile, there has to be a minimum distance, which is nothing but 3.75 D, where D is the pile dia. So from this pile to this pile, we have to give a minimum distance. So 3.75 D means for 50 centimeter dia pile, it is 1.875 meter. 3.75 into 0.5. So that much distance we have to give a clearance from each pile to the centering or sorry to the adjacent or to the neighboring pile. There has to be this much sufficient length is needed. So accordingly, we have to tilt the pile cap so that there will be a proper distance is always maintained. We have to make sure this distance is achieved. So for that purpose, we have to adjust the pile cap. We have to rotate the pile cap like this and have to make sure that all piles are at 1.875 meter distance from the neighboring pile caps. So in that way, we are giving the inclinations, and that's why the pile caps are tilted here and there. So that's about the foundation layout. And also you can see here, along with the pile caps, along with the piles, we are also providing a T-beam. I think the T-beam already discussed by Registrar in the previous session. We are giving the pile cap for the purpose of reducing the load coming to the piles. Because the T-beams are always, T-beams are actually shallow foundations, which we usually provide along with the T-beam. Here you can see a cross section of a typical T-beam detail. It is given here. So the T-beam is actually provided along with the plinth beam here. So T-beams are basically foundations that transfer the load coming from walls to the soil, underlying soil directly, so that the remaining load only going to the piles. So in that way, we can reduce the load coming to the piles, and accordingly, there will be a reduction in number of piles. So if there is a reduction in number of piles, there will be cost saving also. So we can save. There will be savings in the money side also. So for that purpose, we can use T-beam. Now we can see in the foundation design, there will be a longitudinal cross section of the pile we are providing. So here I already said we are providing a double bulb under rimmed pile. So under rimmed piles are basically friction piles. So friction piles is basically piles that derive their capacity, most of the capacity through friction force. Friction force means the interaction between the soil, surrounding soil, and the pile material gives a frictional drag. When we are inserting the pile to the soil for a depth of 10 meter or say 15 meter, whatever be the depth, there will be some soil and the pile material interaction. That means the soil and concrete interaction. So through this contact, there will be some generation of adhesion force, that is we termed as friction force, and through the friction force there will be some generation of some frictional force, and that is actually the frictional capacity of the pile. So if we add the hello Hello, am I audible?
Yes, you are.
Okay. So we can actually increase the pile capacity by two methods, by providing more number of bulbs or by adding the increasing the length of the pile. If either way, if you are increasing the length or if you are adding more number of bulb, we will be getting an increased area of contact. So if the contact area is more, there will be generation of more frictional force. So in both way, we can increase the pile capacity according to the situation. For some site conditions, we can increase the length, but for some other site conditions, either we can increase the number of bulbs. So that way we can go for multi bulb underrimmed piles also. So here there will be will denote the total length of the pile, which is actually the length from ground level to the center of underlying bulb, and then we'll be mentioning the soil strata where the pile is actually resting. So here you can see from the soil report, if you can see the bore log at 10.5, we have clay with N value 1. So we described it here. The pile is resting at clay with N value 1 at a depth of 10.5 meters. Like that, we will provide the information here. Then that's about the pile design, like the pile foundation design. And there is two more part we have to discuss. That is the pile schedule and then the pile cap design, which will be taken by Srishma. So Srishma, can you just continue with the pile cap and pile schedule?
Yes, Kirti.
Okay. So I'll be handing over the session to Srishma. Thank you.
Good evening, everyone. Now we will learn how to give reinforcement in pile and pile cap. First, we will learn how to give reinforcement in pile. Uh, yes. For giving reinforcement in each pile, we need to know three data. First one is the maximum the axial force acting on each pile and the moment acting on pile in both x and y direction. Yes, for this, we have to find first the axial force acting on the pile. Now we are taking only one pile and defining it. Here I'm choosing this pile under this column. So the axial load coming is, yes, 139.7. So we can take 140 kilonewton as axial load. And then we need two other data, which is mxy and mx and my. For this, we are defining it for the moment. Here, we are choosing a combination envelope combo and maximum and minimum, then apply. So this is the column, this is the pile which we chose. Yes, as you can see, it's selected here. So yes, this is the pile. For this pile, the moment in x direction and y direction we have to find. For x direction, it is these are the two values. From this, we have to take the maximum value. It is the 38 kilonewton meter. And in the other direction, it is, yes, 37.8. So we can take it, it also has 38 kilonewton meter. So our axial force is 140 and moment in x direction and in y direction also it's 38 kilonewton meter. So we got all these three data to find the reinforcement. Now we'll go to AADSPRO to find out how many number of bars we require. Yes, here we are taking the column design and designing and detailing. Here we have to input all this data. Moment which we got is 38 kilonewton meter. In y direction also it's 38. At the axial load is, as we saw, 140 kilonewton. And then next, in the main bar, we are starting it with 12 mm dia bar. So here we are giving 12 mm. And before all this, we have to do the settings. in settings, we have to change the type of shape from rectangular to circular. Since the pile shape is circular one, and then save it. Yes. Then we have to give the depth and width. This depth is actually the diameter of the bar. 500. We are giving a 500 dia pile. Yes, this is a 500 dia pile we are giving. So we have to give this dimension here also 500. And yes, as it is a circular one, its width is also the 500. And then the clear cover, we have to give minimum of 50 mm. And then the length of the pile is, we are taking a 10D distance, which is 10 into 0.5 meter depth. So it's 5. Since the pile depth, it's not depth dia, 10D, 10 into 0.5 meter dia of pile. So we are getting 5 meter length, which is the 10D. And then we just execute it. Okay. After execution, we got this results. Here, this is the boundary line. We have to get this point inside this boundary line. If it is outside, it is not safe. If it is inside, then it is safe. So in this graph, we got in the P1 MUX graph, we got this point inside this curve. And also in this P and MUY also we got it inside. And here also we got it inside. And then next, yes, here also we have to check one particular thing, which is percentage of steel. We have to provide minimum 0.4% of steel in a pile. But here the percentage of steel is only 0.35%, which is not sufficient. So we have to increase the main bar, number of bars, to increase the percentage of steel. Here we are giving 3 in X direction and 3 in Y direction, total 6 numbers. But we have to increase the steel in order to achieve the minimum percentage of steel. So we are next giving 4 in X and 4 in Y direction and executing it. Yes, here we got 0.46%. Which is safe, which is more than 0.4. So it's safe. We have to give the even number inside the pile. We can't give 7 number. We have to give an even number. So after 6, we are giving it 8, giving 8 numbers. So here now it all becomes safe. So we can say that we are giving 8 numbers of 12 mm dia bars in this pile. Yes, as you can see, this is the pile schedule. Here, the pile which we chose is this pile, which is P1. Here, this P1, 500 mm dia. We are giving 8 numbers of 12 mm dia bars. This is how we define the pile. Now, next we are learning how to define a pile cap. To connect 2 piles or 3 piles, we are giving a pile cap to connect these 2 piles. So we have to define this pile cap also. We can define this pile cap with the help of AADSPRO and ETABS. Yes, for this, we are taking AADSPRO, and here we are going to foundation and then pile cap design. Here there are several things which we have to given. These are the inputs. First one is axial factored load. Here I'm taking an example of a double pile cap. This pile cap. So here I'm choosing this pile cap. So we have to take the data accordingly. The axial load coming on this pile cap is, it is same as the axial force coming. Yes, we chose this pile cap here. This is the column above. This is the column above the pile cap, which we chose. So we have to take the reactions under this column, which is 289.9, which is 290. And then we have to give the self weight of the pile cap, which we will give later. Then center to center distance between pile. As Kirti said, the distance, minimum distance between the center to center distance of the pile is 1.375D, which is here it is 1.875. And then edge distance we are giving minimum 50 mm. And then yes, pile cap type we can select it from here. Here we are, as I show you, here I am choosing this double pile. So I can choose this double pile cap type as double. For this, we can, if we are doing this, we can select the triple option. As we are doing double, I'm selecting this. And then diameter of, yes, a shear dia we are taking as 10 mm, two-legged, and then tensile bar we are starting with 20 mm. We are giving starting with 16. We can start it with 16. And then yes, column width is our column is 20 by 40, so we can give the data 0.2 and 0.4 meter. And then yes, now we have to give the self weight of the pile cap. For this, yes, this is a section of a double pile cap. In order to find the self weight, we had to get the volume of the pile cap and multiply it with the self weight of concrete. So volume of the pile cap is, as we know, the distance between two pile is 1.875. So we can add the 1.875 with the balance diameter, balance radius, and plus balance this edge distance, which is 50. So 1.1875 plus 500 dia by 2 plus 50. Again 500 dia by 2 plus 50. So we got total 2.475 meter, and then width as 600. Yes, the diameter is 500 and 50 cover in both directions. So we got on 600 width. And we know that we are taking the depth of the pile cap as 0.5 meter. So we can calculate the volume as 2.475 into 0.6 meter width into 0.5 meter depth. So we got 0.7425 meter cube. In order to find the self weight, we have to multiply this volume with self weight of concrete. So multiply this volume with 25. So we got 18.56 kilonewton as self weight of pile cap. Okay, now we entered all the data required and then execute. Axial load. Axial load 289. Okay. Okay. So here we got the result, as we have to provide 5 number of bar as main bar and shear reinforce 5 number of main bar. This 16 mm 5 number we have to provide, and shear reinforcement spacing is 240 mm. We have to give a minimum 200 mm spacing, and the diameter of the shear bar is 10 mm. So here, if this is the pile cap we are designing, then we have to change this. This is the main bar top. This is the bottom main bar. This is the top main bar, and this is the shear reinforcement. We had to change it accordingly. We got 5 number of 16 mm dia bar, and if we are giving 16 5 number of 16 dia bar as bottom bar, we have to give the almost half of the reinforcement in the top, because in bottom the tension is more in bottom and less in top. So we are getting a 5 number of 16 mm bar in the bottom, and in top we have to give 5 number of 12 mm bar, which is almost half of the reinforcement which we provide on the bottom. Then we have to give the shear reinforcement, which is 12-legged 10 dia 200 mm spacing bar, which we got it from here, like 10 mm bar at 240 mm. But we are giving only 200 mm as it is the minimum spacing required. So yes, we are given the main bar and shear, main reinforcement and shear reinforcement. Yes, like this we are designing the pile cap. That's it. If anybody have any doubt, you can ask.
If anybody have any doubt from any of the session, they can by me or Srishma, you can ask. Or any doubts from previous sessions on footing design also, you can ask now. If nobody has doubts, I think we can wind up the session, right? Can anyone respond from student side? Hello?
Yes, ma'am.
Can we wind up the session then? If you have no doubts, shall we?
Yes, ma'am.
Okay, okay then. So we can wind up today's session. Okay.
Thank you, ma'am.
Okay, thank you. Thank you for listening. Thank you.